Building a mobile organism on Earth requires biological engineering to overcome the unrelentless force of gravity. This terrestrial chassis must remain incredibly lightweight to allow for rapid mobility while maintaining the immense strength needed to resist sudden impact forces. Evolution solved this engineering conflict through a highly optimized microscopic composite material. Analyzed as an advanced aerospace-grade composite, the skeleton reveals a level of structural sophistication far beyond a simple static scaffold. This animated diagram of bone tissue reveals a dual-phase material composition. The inorganic phase, hydroxyapatite, provides massive compressive strength, acting as the concrete. The organic phase, type 1 collagen fibers, supplies tensile strength and elasticity, performing the role of flexible steel rebar. This specific marriage of high tensile and high compressive materials allows the bone to absorb massive kinetic energy without catastrophic failure. On a macroscopic scale, we can see how these materials are deployed against massive gravitational loads. This 3D cross-section of a human femur illustrates the first layer of defense, cortical bone. This dense outer shell withstands immense compressive stress, making up 80% of skeletal mass. Pushing past that outer shell reveals the internal, porous, honeycomb-like matrix, cancellous bone. This structure functions as a biofoam, dynamically absorbing shock while drastically reducing the organ's overall weight. By maximizing load-bearing capacity while minimizing mass, this design fulfills the primary requirement for terrestrial mobility. The skeleton is often viewed as a dead, finalized structural frame once adulthood is reached. In reality, Wolff's law dictates that bone continuously adapts its architecture directly in response to the mechanical loads placed upon it. Evidence of this adaptation is found in elite athletes, whose bones fundamentally alter their density profiles to handle extreme strain. Conversely, a microgravity environment removes this mechanical stimulus, leading to a rapid loss of structural density. Bone operates as a continuous, real-time structural calculation, seeking equilibrium with its physical environment. This raises a central biomechanical mystery. How does a solid material actually sense its own physical load? The process begins with piezoelectricity. When the collagen and mineral matrix physically deforms under pressure, it generates a localized electrical potential. This is supported by fluid dynamics. Physical load forces fluid to flow away from areas of high compression within the bone matrix. Osteocytes, the bone's sensory cells, detect this fluid flow and electrical charge. Through mechanotransduction, they translate that physical force into biological signaling molecules. Through these pathways, raw kinetic energy and physical stress are converted into actionable cellular data. These signals summon the osteoblasts, the cellular construction workers of the skeleton. Guided by the data, osteoblasts secrete osteoid to harden and thicken the bone specifically along the vectors of greatest stress. Repeated torque produces asymmetric results, such as the heavily fortified racket-holding arm of a professional athlete. Maintaining efficiency requires an opposing regulatory force, the osteoclasts. Osteoclasts act as a demolition crew, utilizing acid phosphatase to dissolve and resorb bone mass in areas devoid of mechanical stress. This relentless algorithmic push and pull between building and breaking ensures the chassis remains optimally strong where needed and perfectly lightweight everywhere else. Moving past the structural walls, we find a complex landscape within the hidden voids of the cancellous honeycomb. This structural geometry exists specifically to house a massive biomanufacturing payload. The skeletal system effectively protects the body's most critical, fragile liquid payload inside an impact-absorbing piezoelectric vault. This payload is the red bone marrow, myeloid tissue safely suspended within the trabecular voids. It performs hematopoiesis, the continuous manufacturing process for the body's entire blood supply. Within the marrow, hematopoietic stem cells divide to produce highly specialized cellular precursors. This factory synthesizes over 500 billion new blood cells every single day to replace aging and damaged cells. The cardiovascular and immune systems depend entirely on the skeletal system's manufacturing capacity to function. The skeleton serves as an aerospace-grade composite chassis that balances compressive strength with minimal weight. It is a dynamic piezoelectric smart material that constantly computes its own stress loads to rewire its geometry in real time. Simultaneously, it functions as a high-throughput biomanufacturing plant, producing erythrocytes for oxygen transport and leukocytes for pathogenic defense. The human skeleton functions as a self-healing, self-optimizing engine, manufacturing the very blood required to keep the biological machine alive.